I think this is right.
There's just one place.
The program that I have says next Tuesday's optical phenomena,
Yes.
which I'm going to speak about. And the discussion was, by my view, after next Tuesday.
So the Tuesday after the test.
Right. Which I think would be better for you, because if you have to prepare for a discussion and a test. So there may be a mistake on the website, but the program that I have and by which I'm going is microscopy next Tuesday. Microscopy is something that I guess will be interesting for you, but certainly it won't overburden you as a lecture in terms of theory. And then we have the test, and then the ones of you who have to prepare for discussion can prepare for discussion next Tuesday. Now, I have had a constant stream of people today asking things about proteins, and also a few people are intrigued by this question, by this problem with many questions from Izraelashvili, to which I don't know exactly all the answers, to be frank. I can guess what the answers are, and I have given you my guess in the solutions which I gave to Angelica. But because I have so many people asking that, what I'll do next time, now this lecture is very important, so you don't want to spend this time here, but next time, before the microscopy on Tuesday, in a way of preparation for the test, we'll go through the questions from Izraelashvili's book, and to discuss once again how you calculate charge on proteins or particles by using Henderson-Hasselbalch equation. So that will be next time. Don't ask me the questions now, but you can kind of be prepared for the next Tuesday. And what we're going to do in this lecture is finish the electrostatic interactions in colloidal systems, but this time going to alternating fields. And the first interesting thing to note about this lecture is that, as you can see here, okay, you can imagine that this is a full circle. This is a notes-only lecture. You can find this lecture in a textbook. And I'm personally surprised that you can, and then this is good for me because this has allowed me to develop a specific research area. The reason for that is that somehow people have studied constant electrical fields, and somehow the alternating electrical fields have been off the radar for colloidal researchers for a long time, which also shows how important this interdisciplinary research is. You don't want also only to do colloids, you don't only to do some specific engineering, we want to combine different areas and study different effects. So try to understand the theory here. Now there are many cool things for which you can use these types of systems, but we're not going to discuss the cool things now. You're going to tell me about this on the next Tuesday, and the ones that you may miss I'm going to discuss when we come to microfluidics, different types of on-chip operations. So what we want to do right now is to develop the theory for dielectrophoresis, and we're going to start with, again, the usual cool image. Now this is not a cool image yet, and that of course is okay. So what you see here is a colloidal suspension. This suspension has been confined in a very thin layer between two electrodes on the surface of a glass plate. Now you know that the colloidal suspension is white. Now why is it white? We're going to answer this to the next question. If a colloidal suspension gets ordered in a colloidal crystal, it is going to have colors. And these colors are going to come from the long-range organization of these particles. So this is a movie which has been taken by my former postdoc. Now you can see what happens when we're going to apply the voltage through this suspension. So in a matter of less than a second it organized. Then we turn off the voltage, it gets white again, we turn on the voltage. So anytime we turn it on, you can see the color going on, which means that it immediately organizes and orders itself. Anytime let's play this again, anytime we turn off, anytime we turn the voltage off, it immediately goes back into white state, which is disordered particles around. So the application of the electrical field can immediately organize the particles into this long-ranged array of organized particles. Now the question is why? And you probably don't have the answer yet, because what we studied previously is electrophoresis. And electrophoresis obviously does not immediately provide answer to what may happen when you apply alternating fields in a couple of electrodes on the surface. But before we discuss that, we want to go back to kind of just revise once again the most important things from the electrophoresis lecture. Now you can have two cases. There are different expressions from the same phenomena, as you may remember. We can take two electrodes, put in a colloidal particle, apply voltage. The particle itself is surrounded by counter ions. So on average, what you have here, where the line should have been, is closed electrically neutral system. However, when you apply the voltage, the ions start moving in one direction, the particle itself is going to start moving in the other direction. The particle is going to start moving towards the oppositely charged electrode. The reason for its moving, however, is not that the particle itself only moves, it is also that the ions move, so the particle essentially gets to be depleted from ions on that side, so it can film the electrical field from this electrode. Now, if you remember, then we could take the same phenomenon in an infinitely large particle. Eventually, instead of having the particle being in liquid, we can put the liquid inside the particle, in a way. We can take a capillary. We can apply the electrical voltage. Now, the capillary obviously cannot move. But because the capillary is charged, the oppositely charged ions, which are on the walls of the capillary, are going to start moving towards the oppositely charged electrode. And when they start moving, they are going to start dragging liquid. If the capillary is closed, the liquid that we drag in this direction is going nowhere, so it has to come back. It comes back, and then we have this electroosmotic flow inside the cell. If this were an open capillary, the liquid is going to flow out very much as if we have a pump, which is actually used for pumping in different liquids. And then you remember these two formulas, which are essentially the same, but for the difference in the indexes, which just reflects the difference in the geometries. What matters in both cases is the zeta potential, the charge of the particles. Now, this was a 2-minute review of what we studied the previous time. Now, if you are still unsure about something from the previous time, now is the time to ask, before we move on to something that's actually quite different than these electric effects.
I had one from last time.
Right.
Let's say this is water, just pure water. Adjusting the pH, can we change the direction it rotates?
Yes, you can. That's a good question. And you can, if you think about that, you can tell me at what pH you're going to change the direction of movement of the liquid.
7.
Sorry?
7, right?
No, not really. The pH should not be related to the ions in the water, it should be related to the properties of the surface. Right, the dielectric point. Because in this case, let's say the surface is negatively charged, the surface cannot move. The ions are the ones that move. So if the oppositely charged ions are positively charged, they're going to move towards the negatively charged electron. If we change the pH, so the surface goes through the isoelectric point and becomes oppositely charged, then the liquid is going to start moving in the other direction. Obviously, if you're lucky, if you adjust the pH to be exactly equal to the piezoelectric point, the liquid is going to start moving. But you know that, this is a very lucky case, and in most systems you cannot do that, and you cannot adjust the surface charge, especially with surfaces which have, let's say, very strongly charged groups, which have an isoelectric point of, let's say, 2 or 12. So the question is, can you use an electrical force which is going to move the particle, but which is not going to move the liquid? So you remember that if you put a particle here, the particle is going to move in one direction, the liquid is going to move in the other direction. So in the end, you have the particle essentially can move in any direction, depending on where it's in the cell. And the only way to know exactly in which direction the particle is going to move is if it's right here, between the liquid moving in this direction, the liquid moving in that direction, where you have the stagnant layer, where just hydrodynamically the liquid is not moving in any direction. Now the question is, can we use a force which can move a particle but without moving the liquid? And then, even to put it more general, can we take a particle which is not charged and still move it by using electrical forces? And if you think that this is a good idea, actually this lecture is going to give you the solution to that idea. The solution to this idea is using alternating fields. So just a bit of, again, like the usual brainstorming question here. Now, we have the same system as before. And we have the two electrodes, but this time the electrodes are connected to a source of alternating field. So I have said plus and minus, because when this is plus, the other one is minus. And when this is plus, this one is minus. I mean, it oscillates all the time. Now, what's going to happen with the particle? Is it going to move in any direction, left, right? How can it move? What would be the conditions for movement and so on? I'm telling you that you can use alternating fields to move particles, but then kind of when you look at this, do you see the particle moving, and if it moves, in what direction it's going to move?
Both. Right.
Okay. Let's take it one at a time. Now, Daniel is kind of right.
Average minimum.
Right. The problem is that unless the frequency is some ultra low, like below Hertz frequency, the particle just cannot move this far. This is viscous liquid, right? I mean, in order to start moving, it should start moving through the liquid. So if you have a relatively high frequency, it just, by the time it hits, let's say it sees the positive pulse here, it wants to start moving. And by the time it starts moving, you're going to have the positive electrode to be this one. So it would like to move in this direction too, but then it switches again and so on. So it's not move. It's not going to move towards the electrode. Now what's going to do then? Can it move or not? Is there any configuration in which it can move?
If you make the field not constant.
What do you mean make not constant?
Low
So
code change.
Low? Low what?
Local fuse change.
No, it's, I mean, like the field strength will be probably immaterial. I mean, like strong or not strong. I mean, there is something else is the trick here, but I'm afraid Brian knows the answer, so he is forbidden to answer this question. I mean, like somebody, and Ketan, of course, too.
It's an
This is kind of warm now. Okay, I mean, like dipole is about right. But then how, my question is, how can you make this particle move?
I'll use absolute.
Well, if the particle is dipole, it will rotate, but I'm speaking about any particle, which is not a dipole. It is going to form a dipole because the ions are separated from it when the field is applied, and they separate very fast because they are so small. But the question is, how can you make this particle move in any direction? Kind of just some other trick here.
An asymmetrical waveform.
Well, if you have an asymmetrical waveform, this will be the equivalent of applying DC field. And you can do that, but I mean, it's not going to be through dielectrophoretic mobility.
You have to put more than one particle.
Well, I mean, if you have another particle, we'll discuss what happens, but right now we have one particle and two electrodes. How can you move this particle?
Move the electrodes. You bring the particle with it.
Well, you can move the electrodes perhaps, but I mean, there is some element kind of like important here, but I mean, you don't move the electrodes kinetically, but maybe you can do something with the electrodes.
That's pretty close, actually.
It's close. I mean, warm.
Make some electric
field brand new.
Right, yeah, well, yeah, I mean, you know the answer though. But the truth is like that now. Imagine that your electrodes are not like this. They're not parallel, but imagine that your electrodes are just lying here on the surface.
Hey, you move the electrons.
Yeah, well, yeah, I mean, yeah, moving in this sense means reconfiguring them. I mean, like, when you said move, I mean, it also means just kind of jumping them around and so on. But if you move the electrodes, okay, if you situate them like that, then the field is going to be strongest here. And then it's going to be weakest if you just consider kind of like some further out of the in space. So eventually you're going to have a non-uniform field, and thus we're going to demonstrate in this lecture. This non-uniform field can actually move the particle up and down in this configuration. So the particles can either get here in the area where the field is very strong, or it would like to be pushed out and be where the field is very weak. So it either loves the field or it hates the field. Yes, Daniel?
So you could also do it then by having, say, a flat electrode and a pointing electrode.
Right. We'll discuss this during the lecture. Yes.
Those two are exactly the same case.
Which one?
The top and the bottom.
No.
Except that you've moved the colloid outside of the middle. That's the only difference.
Oh, okay. Yeah. Well, yeah. Sure, but right. Sure, but we assume that this is really actually, like from just like also you usually use in physics, we assume that this is a plane parallel infinite electrodes, right? Okay. I mean, I've drawn this electrode just a piece of it, but
you can draw the field.
Theoretically, if you want to, I mean, this is a uniform field, at least inside here. Obviously, if the particle is outside with the electrode, it's going to be the same case. But what I'm speaking about is the case where the electrodes, you have two infinite plane parallel electrodes.
You could think about it as if you just look at the top particle and take it in and out of the page, it's the same case.
If you take this particle out of the page, it will be the same case.
No, I mean like physically towards me and away from me.
Okay, I mean that's already becomes true. I mean, like you have two plane parallel electrodes, the particle is not going to move. You have two electrodes, the gap between which is variable or finite. Then there will be regions where the particle is going to move by the gradient of the electrical field. And the reason for this mobility is again, maybe, but not always, the separation of the counter ions. But this is not the only reason. Any particle can move in this type of geometry, as long as it's polarizable. And now this picture is much better than the theory that we have to go through. Much more informative, but we have to go through that, yes?
Didn't you once say everything is polarizable?
Well, with a very, very specific case which we're going to discuss right now, when the dielectric permittivity of the particle is exactly equal to the electric permittivity of the medium, and the surface properties of the particle are insignificant. So for practical purposes, everything is polarizable in media, even in media. Now the point here is, so let's discuss this in the lecture. I mean, we'll come across that point. I mean, it's an important point. Now the first thing, we just have to derive one very simple formula, which you can find in any book, but I really want to start from the basics here. Now you have a dipole. And everything that we're going to study here goes around dipoles. So the charge of the particle directly does not matter. What matters is the dipole, and how does the dipole come in the particle, we'll discuss a bit later. Now you have a dipole, and you have an electrical field which, let's say, originates here at this point. And you want to understand how this electrical field influences the dipole. What will be the force between the electrical field and the dipole? Now, first you want to know how the dipole itself is going to move. Just for completeness, you can also discuss the torque, which wants to rotate the dipole along the field. Now you can say, okay, like that now. The force that is introduced by a field originating in the origin of the system on a dipole is going to be the charge of the positive side of the dipole. I mean, just again, like if you remember how we discussed electrostatic interaction. the positive charge on the dipole times the multiplied by the strength of the electrical field. Minus, we have minus because we have a negative charge here. The negative charge again multiplied by the electrical field. This is a very basic formula in electrostatics. The force is equal to the charge of the particle times the field. And we have two forces. One works on this side of the dipole, the other one works on that side of the dipole. One is repulsive, the other one is attractive. Now, this formula obviously doesn't carry us much further. So we can say, okay, let's do some math here. Let's take the Taylor expansion of this formula. So we say the electrical field which operates here is equal to the electrical field which operates here plus the gradient of the field times the distance between the 2 points, which in this case is equal to the distance between the 2 charges of the dipole. Now, just for, like we have people of really different background here. Now, this symbol means gradient, which is equivalent to the first derivative with respect to all coordinates of the system. So it mathematically is the operator d dx, d dy, d dz. So this is the derivative with respect to all coordinates. So this is the first special derivative of the field. So this is essentially Taylor's formula. The expansion of something is the first term plus the first derivative times the difference, and so on. Now, when you put in the intensity of the field here, that formula for the intensity of the field, you can see immediately that the first term is going to cancel. This one is going to cancel with this one. And what we end up is we derived, we rediscovered the physics in a way. We derived the formula that the force on a dipole in an electrical field is equal to the charge times the distance between the charges times the gradient of the field. Now, the charge times the distance between the charges is what? It's called what? Dipole moment. So then it's equal to the dipole moment times the strength of the field. Pure physics. Now, the strength of the field, however, is with a gradient in front. So it's not the strength of the field itself, it's the unhomogeneity of the strength of the field. So what matters is not how strong the field is as such, what matters is how strong the inhomogeneity of the field is. And you can see where this formula leads us. This formula describes how stronger the field here is compared to the field here, for example. That's what we're going to use it for. Okay, any questions so far? This is just, yes.
In this case, is the particle going to oscillate? It's not just going to be stationary, right? It's going to oscillate.
Well, it's effectively going to be stationary because the frequency is so hard that it cannot oscillate at that speed. It may try to oscillate, which is essentially trying to do electrophoretic mobility. But for a frequency above a few tenths of hertz, you can't move a particle like 20,000 times like in water, like when you're moving around. The viscosity is so high that, it cannot do that. So we're discussing only the non-oscillatory component, which is present at any frequency. This component is not dependent on the oscillation, it's dependent on the dipole moment of the particle. So the force on the particle is going to be equal to the dipole moment times the gradient of the field. So far, so good. Now, where does the dipole moment come from? Though, assuming that you have a particle without dipole moment in the original case. Yeah, technically, the counter-ions may contribute to the dipole moment, but what is the physical phenomena which makes the dipole moment existing? If you remember van der Waals forces. Polarization. Exactly. If you remember van der Waals forces, anything in an electrical field gets polarized. That's how the atoms attract each other, because they polarize each other and then they start attracting. In a very similar way, the field is going to polarize the particle and induce a dipole moment in the particle. Dipole moment in the particle. And actually I have copied this part here from our lectures on van der Waals forces. I mean, you can see how beautifully everything fits together if you think in more general physical terms. If you remember, when we have been discussing van der Waals forces, we discussed this sphere, which has a polarizability which is equal to 4 times pi epsilon epsilon 0, where epsilon is the solvent medium. This difference in polarizability here, polarizabilities, and then the volume of the particle. And if you remember, the discussion there was that this particle is only as polarizable as the difference between its polarizability and the polarizability of the medium. Effectively, it can be positively polarizable or it can be negatively polarizable. It can be, the dipole moment can follow the field, can be against the field or can follow the field depending on how well the media polarizes. And let me just finish here. Then usually in terms of when we have particles in dielectric medium, this expression is written in a little bit different way. Now if you remember, the dipole moment of the particle is the polarizability times the field. Then what people like to do, instead of using polarizability, they would like to split the polarizability into a few components. Now 4 times pi epsilon epsilon 0 epsilon 1, where this is the media, is kind of a constant term which cannot change. But then this term k here, which is the difference of the polarizabilities, is also called Clausius-Musotti function, and it is the one which gives the polarization effects. It is the one which tells us whether the particle is going to be more polarizable, less polarizable, or in some very, very special case, practically not important really. If the polarizability of the particle and the media is exactly the same, then you're not going to have polarization of the particle at all. Now, just a test question here. Test means kind of like who remembers best the lectures before. Now, how can you experimentally determine which particle would be about the same polarizability as the media? By using what method?
You need the spectroscopy.
Right. Actually, it's refractive index. But you know that in reality, you don't have particles which are the same refractive index as the median. So every particle is going to be polarizable all the time, which means that the electrophoretic force is going to operate all the time, unless you take very, very special care, which you can do really, to make the particle exactly as polarizable as the median. Okay, so again we have the dipole moment here, which includes the Clausius-Musotti function. Before you ask question, just let's go one step further and actually derive the expression for the dielectrophoretic force. This is the two equations that we derived so far. The force on a dipole is equal to the dipole moment times the gradient of the field. The polarizability of the particle, I have put it here as effective polarizability of the particle, is equal to this term 4 times pi epsilon epsilon 0 constants times the Clausius-Musotti function, which is the difference between the polarizabilities of the particle and the media, times the volume of the particle times the strength of the field. Note that this is the strength of the field, not the gradient of the field. The particle is polarized by the field. The dipole interacts with the gradient of the field. So then we combine everything in this equation here, just plug in the effective polarizability. The terms field times the gradient of the field actually gradient is derivative. So the function times the derivative of this function is actually equal to the squared, to the derivative of the squared function. And we have this parameter 2 here, which decreases the parameter 4 to 2. Right? I mean, I'm going to have 2 here, which cancels with the 4 on top to make the coefficient 2 in front. And this is the formula for dielectrophoretic forces. As you can see, it's very different than the formula for electrophoretic forces. It does not depend on the charge of the particle. It is more complex. And to discuss the complexity here, and it depends on something which is relatively complex, which is the gradient of the field. But then experimentally, we have enormous advantages here that I have also spelled out here, this k parameter. I have spelled out this k parameter here in this formula. And then let's just go one step further before discussing questions. Now, what happens when the polarizability of the particle is different from the polarizability of the media? We can have two cases. Polarizability of the particle is higher or polarizability of the particle is lower. You can immediately see that when the polarizability is higher, the Clausius-Moussotti function is positive. The Clausius-Moussotti function is negative in this case, so the force is also going to be negative. We'll discuss what this means in a second. And you can see that this force is kind of limited. If you keep on increasing the difference in polarizabilities, you're not going to increase the force, right? If you have a very polarizable or very unpolarizable particles, you have the two limiting cases where the Clausius-Moussotti function is either goes to 1 or to 1/2, which actually tells you that the negative force is can never be as strong as the positive force. Physically, what this means is shown here. Now, which is the case when the particle is more polarizable than the media? This one or that one? Now, that's a question of a little bit more bigger difficult. So,
Which one is the medium? One or two?
No. I mean, yeah, two is the particle. Okay. One is the media.
And what was the question again?
The question is like that. Now, you have these two cases. This is the strength of the field. This is the dipole moment. Which of those cases corresponds to each case here? Up or down? Which one?
It's down, right?
It's up.
Ha!
But
It's down.
epsilon the or is 0, the higher the closer to the top of the arrow is the field higher?
Yeah, I mean, if you just kind of have a view, let's say this is plus, this is minus. I mean, like you don't.
But I thought it depends on the gradient, right?
Right, but no, but this is what I'm. This is the dipole moment which is induced in a particle by a field. So if you can now you have two particles here, one of which corresponds to this case, the other one corresponds to that case. So which is the case of the Clausius-Moussotti function being larger than 0, and which is the case of the Clausius-Moussotti function being smaller than 0?
But you can't give us an electric field. You'd have to give us another one because we need a gradient.
No, I mean I'm not. What I'm asking you here now. This is the dipole moment in the particle. This one. You don't need a gradient here. You understand? The gradient. So we're not discussing the force. We're just discussing what would be the direction of the dipole. Just kind of in which direction the dipole is going to face. Is it going to be facing the same direction as the field or the opposite direction? You understand? Kind of the polarizability of the particle. Okay, that won't work here. The polarizability of the particle is this term. It is determined by the Clausius-Moussotti function. The gradient all comes into play when we discuss the force, right? The question is, when the dipole is going to face in the same direction as the field and when it's going to be in the opposite direction as the field.
K is greater than 0, it'll go with the field.
Is it? So you're telling me that that's not the right case, or this is the wrong case? This is the wrong case, or this is the right case, which I have drawn here?
I'm saying I'm saying that's the wrong case.
No, I mean, it's a little
The
bit.
dipole moment is directly related to K and
Right.
E naught. The
Ah.
electric field.
Right, but the way the dipole is defined, I mean, just if you assign, let's say, plus and minus here, and if you want to understand what the plus and the minus on the particle is going to be, in the case when the polarizability of the particle is higher, the plus on the particle is going to face the minus on the field. That's how it works.
Okay. I don't think there hasn't been a convention with the electric field plus or minus.
Yeah,
It's
it's
defined.
It's kind of been.
okay. This is a bit technical.
Okay.
Until you don't need it. I mean, the point is that
They're
if the
opposite.
field, if you define the field as plus and minus in one direction, the dipole moment, in the case when the particle is more polarizable, is going to actually face opposite to the field. So the plus and the minus on the particle are going to be opposite to the plus and the minus on the field. I mean, you can't measure that, or you don't really. It doesn't surface in the formulas afterwards. But I mean, just physically, the particle gets polarized in a way that the plus on the particle faces the minus of the field, and vice versa.
So that the sanity check is like if you go vacuum, which is the lowest epsilon R that you can have, then you would have your charges fade. That makes sense, right?
If you have the lowest epsilon that you get, the particle is
in vacuum, the charge
Right.
is going to face towards the opposite electrode.
the effective dipole moment, which you're going to get, is not going to come from the vacuum. It's going to come from the media. Let me demonstrate how it works. Now imagine that this is the field. This is your particle. You have nothing here. So this is the minus on the field, and this is the plus on the field. Now if you measure the field inside, the minus is going to be here and the plus is going to be here. So it's going to face in the same direction as the field. If this is a polarizable particle, if you remember, the pluses would like to come towards the minus, and the minuses want to come towards the plus. So then the particle is actually going to have plus here and minus here if this were polarizable. So if this were also polarizable media, if you put a plus here and a minus here, so now imagine that this is vacuum and this is metal, for example. When you put metal, the electrons on the metal are going to immediately go towards the positive electrode, and you're going to have a plus here. That's how it works, technically. Of course, you don't need this kind of like in terms of using the formula. I mean, this is just a reminder about physics.
And when is it going to be oppositely polarized?
Well,
Like
oppositely,
in the same. I'm sorry. Like.
I mean, like the true polarization, which is kind of, let's say, the right polarization, when it's more polarizable in the media, is the case where K is larger than 0. This means that you have a particle which is more polarizable than the media. In the other case, as you see like epsilon 2, the one of the particle, is larger than epsilon 1, the one of the media. So the particle is more polarizable than the media.
No, but what does that mean? Like, how do you interpret it? If you.
You can think, well, this means that that eventually okay, I mean, like when we go to the interaction, this means that the particle you would like to get in the strongest field as possible when we discuss the force. This wants that the particle likes to be in a strong field because it gets polarized, and polarization, if you remember, means gain of energy for the system. Gain means release of energy, kind of. It's energetically more favorable for something that's polarizable to be polarized. Okay, now complex as it is, I mean, it works very simple, and there is lots of text here, but I think you need it, especially after all the complex thinking on the previous page. Now let's kind of discuss this formula in terms of practical effects and what it tells you and so on. This is the formula here. K is this one, which relates the difference in polarizabilities. Now, just to kind of again like think about how it works, I always like using this case of two electrodes with variable gap. Now the field, let's say, is in this direction. Now this is the momentary field, otherwise it oscillates. But in any case, the field is going to be perpendicular to the, let's say, this if this is this radio, perpendicular to the plane between between the electrons. That's where the field is. That's where the field is. The gradient of the field is going to be in this direction. The field is highest here and it's lowest here. The closer the electrodes, the higher the field, right? So this case is it's very good for explaining, because the field and the gradient of the field are actually perpendicular. Now let's examine the formula here. The dielectrophoretic force, okay, let's start with what is simple, proportional to the particle volume. That's easy. Now, proportional to the electric permittivity of the medium. Now, sorry, this should be E1. Excuse me. Proportional to E1, that's easy too. So far, so good. I mean, now, what do we have here? Now, first of all, before we go actually there, now let's discuss this term, gradient. Now, the field faces this way, the gradient faces this way. So this means that the dielectrophoretic force is directed along the gradient, which in general is not the collinear of the field. So you may calculate the field lines, but the force may not be along the field lines, it goes along the gradient, it goes along the strongest field intensity or weakest field intensity, which in this case is here. And now then, we have the most complex part, and I mean, if you think that this is complex, wait for a few more slides when we're going to discuss the frequency dependency. But I mean, that's what gives us so much power in this method actually. Now, positive dielectrophoresis, this is the definition which people have defined in dielectrophoresis, is one where K is larger than 0 or epsilon 2 is larger than epsilon 1, when the particle is more polarizable. If it's more polarizable, it wants to be in the highest field intensity. It likes being polarized. If we have the other case when the particle is less polarizable, the particle really doesn't care about the field. It doesn't get polarized. But the fact that you have a particle here means that you are substituting some media which would like to be in the field better than the particle. So the effective result is that the particle is going to be pushed out of the areas of highest field intensity. So this means that if you can change this parameter in some way, and I'll tell you the way in a second, you can either pull the particle in the middle between the electrodes, or you can push it out of the gap.
Can you draw the dipole moment on those spheres, just to reaffirm what
let's say if the field is in this direction, then the sphere which is going to go down is going to have the dipole moment facing this way. And this sphere is going to have the dipole moment facing that way. If you would like to think very mechanistically, let's say this is plus and this is minus. Now let me demonstrate immediately what all those theoretical complex physics means if you just think in terms of plus and minus. Now this is plus and this is minus. If we keep to the same convention here, this is going to be minus and this is going to be plus. On this particle we're going to have the minus here and the plus here, right? Now imagine that you are this particle. It gets attracted to this electrode and it gets attracted to this electrode. So the closer it can get to the electrode by getting here, the better. If you are this particle, you have minus facing minus and plus facing plus. You're obviously going to hate that, so you would like to get out of there. Of course, this is a little bit simplistic, but that's how it works. Can you imagine that?
Oh, that's very good.
White face. Now, maybe I don't know conventions for dipoles and so on. Some people may define the dipole facing the other way, but I'm using the convention where you have plus to minus, and that's it, kind of just where the plus and the minuses are. When it comes to physical convention, people may draw the dipole to be collinear with the field, but then the convention for the dipole would be that, I mean, the vector is going to, in this case, going to point from in the inverse direction of the field. If you just think in terms of pluses and minuses, the plus on the particle faces the minus of the field, and that's the one where it gets sucked where it likes to be there. Yes, Daniel was first. And
Is this hold for just electrophoresis too?
good question. You want to tell me why? Can we have a constant field? Do it work like electrophoresis? Yes.
Yeah.
I mean, I was about to tell you on the next slide, but you.
Oh, sorry.
Yes, it's true both for constant and AC field.
So
Now, why do you want to use AC field? I'll discuss this in the next slide. Do you have the same question or? Okay. Okay, so this lecture has really taken into like kind of like mind-boggling case. Okay. So now this is true, as Daniel said, for both constant and alternating field. It's going to get polarized in any field. Now the fact is that polarizability is very fast phenomenon. Now the particle cannot move around electrophoretically because it has to move in physical. But moving of the electron is so fast that it's going to always going to get polarized. Unless the frequency is high, we'll discuss that. So then the question is, why did we have to go all this trouble and discuss all this field? What is the difference between AC and DC? Why, for example, we want to have this configuration and work with AC field instead of DC field? And this immediately gives us to the advantages of dielectrophoresis compared to electrophoresis. Now,
In this case, in the previous slide,
Right.
is the particle going to be pushed like out of the paper or inside, like perpendicular to the paper?
it's going to be in the plane of the paper. So the electrodes are facing you out of the paper.
But it shouldn't because of the like.
No, you have two semi-infinite electrodes which are like that. And the paper is a cross-section through perpendicular to the electrodes, right? Okay. So I mean, in this case, because it's a two-dimensional system, the way I've plotted it, this dimension has no importance. I mean, it's semi-infinite. Consider it unimportant.
But the formula that you give in the slide
Uh-huh.
is does it have a cross product or a dot product in that case? That's what I want to know.
Does it?
Like in the Taylor series.
You mean you have the gradient there, which is a three-dimensional derivative, right? Or wrong? Is what you mean?
Like you have U into delta E. Does
Right.
it have a dot product? It should have a cross product because it's a vector that we're getting. But in that case,
there should be there is no cross point. I mean, this is just the derivative.
It's a dot product and you don't get a vector.
So when you apply gradient to a vector, you get a scalar. Okay. So
okay.
now, I mean, this is important. So let's leave the mathematical stuff for now. Let's discuss this point first. Now, you have the same two electrodes. In principle, the particle is going to have the same dipole-induced moment and force when you apply both constant and alternating field. Now, why do you want to apply alternating field? For dielectrophoresis, both constant and alternating field work the same. For electrophoresis, only constant field works. Electrophoresis cannot make the liquid or the particle move with the frequency of the field. So why do you want to use alternating field rather than constant field? Now, first of all, with constant field, you have what? Electroosmosis and electrophoresis. Now, if you take these two electrodes like that, put water inside and some particle, and you apply constant field, this particle is immediately going to go on, bump on the oppositely charged electrode and coagulate there, which is only part of the problem. But then you know also that the liquid is also going to start moving around, and the direction in which the particle is going to move is, I mean, you may consider it random. You're just going to see liquid moving, particles moving, and so on. When you apply alternating field, the particle is going to move only in this direction, and that's it. Now, this is the first good thing. The second good thing is that if you work in water, you can apply only how high voltage across water. Who knows some electrochemistry here? How many volts you can apply across water? And what happens if you apply more volts? Daniel is the electrochemical expert here.
About 1.2 versus MSC, I think.
Yeah, one point something is the right answer, but the practical answer is, let's say, about few volts to 10 volts or so, because you have over voltage.
Depends on the pH. Too.
Right, but the point is that you apply more than a few volts across water and it starts electrolyzing, bubbling. And this is certainly not something that you want to happen in your microscopic nano device or something like that, right? The next good thing is that it works with any particles, because it's a polarizability driven effect. Charge, it may not be charged, and it's still going to work. And finally, and that's where kind of, I mean, like we haven't reached the land of Mons yet in terms of theory, we have the frequency dependence of the force. The polarizability, if you remember, was frequency dependent. So what we're going to do next, actually, we're going to explore how this frequency dependence changes the properties of the force. Now, just a couple of important geometries. If you have a single wire-like electrode, the particles are going to be attracted to the wire. This case, if you have this gap, the particles are going to be attracted to the gap. So you can attract them towards the electrode, or you can attract them towards a gap. Now, any questions here? Now, if you have questions about the formulas, let's not discuss them now because we have to move on. Just physical aspects. Okay, I mean, like, especially after I scared you about the frequency dependence. So let's go towards this direction. Now, immediately comes a simple question. Now, if we have metal, what's the polarizability of the metal? It's about infinite. Now, in this case, you don't have really polarizability, you have conductance. The exactly same formula which we have described already also works with conductances if we have conductive media. Instead of polarizabilities, you can put in conductances here, and you're going to have the same formula. Now, what would be interesting is that if we have metal, so the conductance of the particles is infinite, then you're going to have the maximal dielectrophoretic force which you can have, which, as you can see, is fairly tamed force. It doesn't go to infinity. It goes just to having this coefficient here twice as large as the usual case. So far, so good. So we know that metallic nanoparticles or nanoparticles are going to be attracted always. Now the question is, what happens with dielectric particles? And if you remember, we have been discussing different effects with electric particles. So let's taking this one thing at a time. Now, first of all, let's discuss the case. Again, we have not reached the dreaded frequency dependence. What happens when you have a particle which is a shell-like? And this may look exotic, but this is very important case. You can say, well, I mean, I have one polarizability here, another here, and the polarizability of the media all around. So I'm going to bundle these two polarizabilities in an effective polarizability, epsilon 2 prime. And then I can recalculate how this epsilon 2 prime is relates to these polarizabilities. And I have this complex formula, which includes polarizabilities and radius of the particle on the shell. Complex as it is, it's very simple for calculations. And why people are interested in these formulas? Because dielectrophoresis has traditionally been used. That's why instead of calling it scientists doing their job, it has been studied by people who move biological cells. Biological cells are obviously a shell of a lipid, which has one polarizability, around the contents of the cell, which has another polarizability, which is different from the environment. So that's how people calculate polarizability of cells for the practical applications of moving biological cells around. And now we come to the real world, and in the real world the polarizability is very complex. Now we have complex frequency dependence of the polarizability, and in this case what do these i's here, imaginary numbers, mean when we have polarizability or any other phenomenon? Angelica here should know, for example. What, for example, in rheology, what is the component of the rheology which has I in front, which has what is the imaginary component of elasticity, for example?
For G double prime, the
Right.
charge,
Which is what?
the loss modulus.
It's viscosity.
Oh, for the
Right.
right.
So this is, for example, in a case where we have a solid body, and if you compress the solid body, it's going to have a real, let's say, response, which is elastic response, and it's going to deform, which is the imaginary response, in the sense that it's not never going to come back after you squeeze something viscous. In the same way, polarizability has the real polarizability components and imaginary polarizability components, which are actually related to losses. You know that when you put something in a microwave oven, what happens with that something? Heats up. So this means that when you put stuff in alternating fields, depending on the frequency, the stuff may get heated up. So you have eventually some of the field is used to polarize the particle, some of the field is used to heat it up, which is lost energy. Now this lost energy is usually related to conductance, which is the stuff which gets hot in microwave oven. Conductive or non-conductive?
Conductive.
Right. That's why you don't put like metallic stuff in microwave, because it heats so much that bad things happen. So the more conductive, the bigger the loss. So that's why you eventually the real polarizability of real particles have the component which responds to polarized, and then this component which responds to losses due to conductance. And then, if we put this in the formula, we have the complex polarizability here. You don't want to work with complex polarizability. Good people have solved these equations and has come with this equation, for example, which somewhat approximately describes the real part of the polarizability, because this is what matters in the equation. If you lose energy, it's not going to generate a force. So that's why in the real equation, for real cases, you have the real part of the polarizability of the Clausius-Mussotti function. The Clausius-Mussotti function then includes epsilons, conductances, and frequency here. So depending on the frequency, the Clausius-Mussotti function can be larger or smaller. Even more than that, depending on the frequency, the Clausius-Mussotti function can be positive or negative. Which means that if the polarizability of the particle and the environment does not change in the same way, at some frequency you may have attraction, at another frequency you may have repulsion. And this is very important physically. Just imagine what happens in this case. You have a particle which is attracted to the gap between the electrodes at some frequency. You change the frequency and then the particle is repelled. From your viewpoint, from the viewpoint of an experimentalist, all you do is you just rotate a knob, right? And your particle moves up and down, or it may stop just by changing the frequency. So you have a very universal, very precise way to control the position of a particle, for example. And this is some experimental results for polystyrene particles in water. Now, polystyrene would like to be repelled out of water. It has lower polarizability, but not at low frequency where it has what? Counterionic atmosphere, which can also move and also generates a dipole moment. So if you plot the force of a polystyrene as a function of the frequency and electrolyte concentration, higher electrolyte, higher frequency, you're going to find out that the polystyrene particle is going to be attracted to the gap at low frequency and low electrolyte. And it's going to be repelled from the gap at high frequency and high electrolyte. Now, what is the effect of the electrolyte here? Why does
Over the medium.
right? It changes the polarizability of the media. I mean, like when you dump in too much electrolyte, the polarizability of the particle, which is not too high in any way, actually gets the lower at any frequency because the media is so polarizable and conductive. So if you want to manipulate dielectric particle like latex, you want to put it in low conductance media, which means pure water, and you want to have to use low frequencies. If you dump salt in the solution, you're going to decrease the responsiveness, and you're going to cause the particle to be repelled. But again, this is a very powerful, very easy tool. I mean, you just rotate something, a knob, and your particle moves the way you like. Okay, questions?
The formula on the previous page is epsilon 1 also the frequency dependent one or just the DC?
Epsilon 1 would also be frequency dependent, would also be frequency dependent, but it's going to be frequency dependent in general in kind of like, let's say, in a tamed way. So if you assume that epsilon 1, the epsilon 1 is not that important, I mean, that's how people calculate. I mean, you still have epsilon 1, but I mean, like, it cannot change the sign, for example.
But if I take like water that has a it varies from 80 at DC to 2 or 3 at
you're right. I mean, this formula is an approximation. I mean, in the real formula, you have to take into account also the complex dependence of epsilon 1.
And the loss also depends on frequency.
Yeah, I mean, you're right. I mean, the real, again, like this is the simplest formula that people could come up, assuming that, let's say, a particle is polarizable and so on and so forth. Essentially neglecting the polarizability of the media in this frequency range. So, I mean, that's of course you can have more complex formulas and you can calculate everything, but it goes into complex calculus. Maybe the effect may be much more complex.
So you get the imaginary parts when the frequency of the AC is out of phase with the dipole?
Yeah, it's the imaginary part means that the let's say the position of the dipole is not in phase with the direction of the dipole is not in phase with the direction of the field.
That's what I was trying to say. Right?
Kind of, let's say the field is in this direction, and ideally the dipole faces this direction, but because it needs some time to move from one direction to the other.
Yeah.
By the time the field changes, the dipole cannot really reverse itself.
So it's
So essentially, it may be that at very high field, the dipole is out of phase with the field, and that's what's going to change the polarizability. That's what happened. This is the real phenomenon. This is the equivalent of conductance, actually, because this is going to increase the losses. That's why these effects get important at high frequency, and that's why microwave photons operate at high frequencies initially. They're really high frequency devices, you know that. They're, I'm not sure, gigahertz, terahertz, and so on. Right. But I mean, that's why they operate at very high frequency, because that's where the losses are highest. I mean, that's where the dipole cannot follow the field. So that's what imaginary component means. Okay. Angelica, okay.
What's the physical meaning of the relaxation time?
This, very good question. I mean, that's the, this is the, like, I mean, essentially 1 over this time is the frequency where we have the so-called crossover frequency, where the force changes from repulsive to attractive. You see that if you have this one, let's say this frequency is equal to 1 over this thing. This is the case where you're going to have 1 plus something, plus or minus something, and essentially this inverses the sign of the whole function. So the so-called crossover frequency is actually the one which, if you plot the whole function, where the force goes from negative to positive. Now, calculating this frequency may be a bit tricky, because you need to know the polarizabilities and the conductivities of this specific frequency, and I mean it's a little bit of a complex process, but you have this crossover frequency which is related to the relaxation time. As a part of your homework, you're going to exercise that kind of, just calculate this function for a few parameters and see how it works. Okay, we have one more force to study today. Just as an example of how you can use a force, you can have various combinations of electrodes, and you can have something which typically is a live cell, for example. Now, if you calculate just the conditions for equilibrium, I'm not going to details here because time is getting short. If you calculate the conditions for equilibrium, you're going to find out that the only way you can have something in equilibrium is by using repulsive forces. You can't attract an object because when it gets closer, the force increases, so it always jumps into contact, for example. Like if you remember the Izraelashvili apparatus, where you can only measure repulsive forces, because you can never have equilibrium and attractive forces. I have described this mathematically, how you derived this condition for equilibrium, but you have the gravitational force pulling this particle down. You have repulsive force pushing it out, so you can levitate it. You can make this particle, people in NASA are studying similar things, for example, although not in water. You can have this particle or biological cell kind of float around and stay where you want it without contact with anything. Levitation of kind of use of this force. Okay, questions here? Now we want to very briefly, I may finish a little bit next time if necessary. Now,
On that,
forward one here.
in that one.
Uh-huh.
I look at the A on the right, and so is there voltage applied to the electrode on the upper left?
This is essentially this electrode here, for example.
No, I'm sorry, the one up
This one.
A, yeah, that one.
Yeah, this is applied here and here. It's an alternating voltage.
Okay, and then also there's a voltage applied on the other.
In this case, the voltage applied here and here. This is a ring.
So that and on A, both
Right.
top circular electrodes have voltage applied on
It's a
them.
ring,
Yeah,
Bob.
No, this one's a ring.
It's a cross.
It's a ring.
It comes in.
Oh.
So it's a ring,
A donut.
something like that.
Yeah. How does that particle get in there?
Well, I mean, you can drop it in somewhere, right?
So isn't it being repelled away from it?
It may be, but you also have gravity pulling it down, right?
Okay.
So and here, once it gets to be here, it's out of the field, so there is no force.
But there's electric fields coming like this.
Well, there will be fields coming like that here and so
Trying to keep
on.
the particle out from
Yeah.
getting in there, though.
Well, I mean, well, but the field, you see, there is this region of lower field. If you calculate the lower field intensity, this region here is lower field intensity than this one, right?
But on the outside of this is even
Uh-huh.
lower intensity. So how do
Right.
we ever get in the inside?
But in order to get to the outside, it has to get even further out. The force is going to be smaller, and then you have gravitational force pulling it down.
Okay.
So gravity would like to pull it down as low as possible, right? And the lowest case here, of course, if you take it out, it's going to drop out of the ring here, right? If you apply too high voltage, you can push it out, and then it's going to fall out. But if the voltage is just high enough to repel it here in this region, but not high enough to repel it from this region of lower intensity, it's going to levitate there. I mean, and then people really do that. You can take a biological cell. You can make this also on chip. We're going to discuss this actually when we reach chips. You can make this by electrode geometry on a chip, and you have a live cell, and you can raise it above the chip, and then you can move it around. And you can make a factory where, I mean, you see that. I mean, these are very cute movies where cells are kind of like being moved around like in a factory conveyor. Now let me start with this first though. I mean, you can ask questions later. Let me finish this lecture. It's important. Now, so far we discussed one particle. And it has an induced dipole. But then what happens if we have many particles? Each particle has its own induced dipole, right? So then these dipoles, if you remember, dipoles interact with dipoles. So what I have done here is I have actually, this is from the Mike van der Waals lecture, how dipoles interact. The strongest interaction is when the dipoles are arranged themselves like that in line. And this is exactly what these particles would like to do. They would like to arrange themselves in line so their dipoles interact in the best possible way. And this is called chaining force. Which brings the particles together. We are almost out of time, so I mean, this is just an experimental example of what happens with the chaining force. I have these derivations. I'll not go through this now, but I'll review the chaining force when we start next time. But this is experimental data again from my postdoc, and this is what happens in the first movie when the particles get to be red and white. When they are red, an intermittent state of the organization is this formation of particle chains because of the dipole attraction. So I'll go to that next time. Let me kind of finishing this off. Let me try to summarize all the forces that we have studied this far. You can have chip. I have used two particles here to illustrate all forces. Two electrodes. The electrical field goes this direction between the electrodes. The gradient goes in this direction, perpendicular to the electrode. If you apply constant voltage, the particles can move left and right towards the electrode of opposite charge. If you apply alternating voltage, the particles can move up or down because of the dielectrophoretic force. And finally, when you apply any voltage, typically, however, it will be AC voltage, these two particles are also going to attract each other in what's called chaining force.
Shouldn't the arrows kind of be drawn the other way?
You mean attractive?
Yeah.
Yeah, but I mean, they become too ugly to make them like that. So the force, there is a force which operates like in this direction, it can be this direction and so on. Obviously the force, I mean, like this is a schematics of how the force works, right? If I draw it the other way, I mean, it would look like it looks weird and you won't understand it. Obviously you understand what's going on here. The point here is that you can have particles and you can manipulate them in any direction, anyway. You can attract them to each other, levitate them, move them left, right, up, down, measure the electrical properties, and of course use them for different manipulations. Okay.